Okay, this is part 2 of the water waves lecture. Please make sure that you take a look at the short video clips that I've posted regarding the ripple tank demonstration, the two-source interference pattern that I referenced in those short film clips. Also take a look at the applet that I used. I posted it for you as the applet that I used in one of those film clips. Okay, here's how we form that interference pattern, and here is ultimately how we explain it mathematically. So we have right here the surface of the water, and then I have what I refer to are two coherent point sources of circular water waves. When you say the word coherent, this then means that the water waves are identical to each other in every way. That is, they have the same wavelength, they have the same frequency, same amplitude, and so on. In addition to that, the two sources are tapping the water in phase. They're tapping the water in unison. They're not out of phase, for example, like so. Instead, they're tapping the water like this. Okay, so let's say that right here are the two sources, like so, and like so, and then propagating outwards from each individual source are a series of circular water waves. Okay, I'm going to draw two for each in order to explain the basic idea as to how the pattern gets built up. Okay, so let's say that right here is a circular wave crest for this source. Here's a second circular wave crest like so. And then I'll do the same thing for the second source as well. Let me draw this circle here a little bit better. As you'll see, this diagram gets a little bit messy fast. Okay, and now for the second source, let's say that here's a circular wave crest like so, and then here's a second one. Like so. And then notice that there are portions here within the ripple tank itself where you have a crest and a crest overlapping each other. That would be, for example, right here, right here, right here, and so on. So if you have a crest from one source overlapping a crest from a second source, that then gives you a really big crest. That's a region of total constructive interference. This would then be an antinode. So these purple dots right here, these are where we have crests overlap. This is, as we say, a region of total constructive interference. And those points there are referred to as antinodes. Okay, now I didn't draw any troughs, but let me just go ahead and draw two troughs here, one for each source. So in between this crest and this crest for this source, there's a trough, for example, right here. Okay, and then for the second source in between this crest and this crest, there's a trough, for example, right here. And then take a look at, for example, this point right here. So that point right there is where you have a trough from one source overlapping a trough from another. So then therefore you end up with a really deep trough like so. That's still a region of total constructive interference. It's still an antinode. So these black dots, there's only one of them on my diagram. This is where we have troughs overlap. And then ultimately, once again, this is where you get an antinode. Okay, but then also take a look, let me get a different color here. Take a look at, for example, these points that I'm going to draw in red. Say right here, for example, like so, or here, or here. Let's see, one more. Right here. So this is where you have a purple crest overlapping a black trough like so, and then the two cancel each other out completely. This then means that the water is completely flat right there. That is then therefore referred to as a node. So here in red is where you have a crest and a trough overlap. They cancel each other out. So this is a region of total destructive interference. This is then therefore referred to as a node. Destructive interference. So those are nodes. Now, of course, when you draw this on the board, it looks horribly complex, so do make sure that you take a look at the simulation video that I've posted for you and the actual physical pattern itself that I formed in my ripple tank. Pause the film at this point in order to access those videos, and please take a look at them. Okay, now when you first of all draw out this pattern, once again, it does look horribly messy mathematically, but actually it's not. Ultimately, describing where you have an antinode or a node in the ripple tank itself is rather easy to do. The in-between positions we don't care so much about. We're only instead concerned with the locations of nodes and antinodes. Okay, here's how we go about finding the mathematical conditions that are necessary to first get an antinode and then secondly a node. Okay, so first of all, the condition necessary to get an antinode. Okay, now there are some definitions here as I proceed. So let's say right here is the first source. This is usually just referred to as S1. Okay, here's the second source. We'll refer to that as S2. And then we have some point in the tank. This point in the tank is usually just referred to as point P. So what is the condition necessary in order to get an antinode at point P? Okay, now S1 is some distance away here from point P. This is usually just referred to as R1. And then right here, this is this distance that S2 is away from point P. This is referred to as R2. Okay, now in order to get an antinode at point P, the following has to happen. So imagine, for example, a sine curve, like so, propagating outwards from S1. It then travels this distance in some time. And let's say at the time that we look at arriving at point P is a crest, like so. Now at the exact same time, from a wave that originally started at source 2, you also have to have a crest from that source arriving at point P at the exact same time, like so. So here are two crests then which completely overlap each other to produce an antinode at that location. In order for this to happen, the following then therefore has to occur. Okay, what I'm going to draw is a dotted line like so down to this location here. And I'm going to draw this dotted line such that this distance here and this distance here are the same. Therefore, this distance here is the difference between R2 and R1. This is usually referred to as delta R. Delta R is equal to R2 minus R1. And this is given a name. It's referred to as the path length difference. Okay, now, in order to get an antinode at point P, the following has to happen. If I have a sine curve coming out of S1 at this instant in time, then coming from this point here, which is the same distance away from point P as S1 is, also has to be a sine curve, like so. Such that then these two sine curves travel the same distance in the same amount of time. They then arrive at point P together entirely in phase. Therefore, they constructively interfere. The only way in which this can happen is that right here in the space delta R, we could have the following: a single wavelength, or two wavelengths, or three wavelengths, or four wavelengths, and so on and so on. So then therefore we end up with a little pattern equation here that explains the condition that is necessary to get an antinode at point P. In the path length difference, we have to have a multiple of wavelengths. So the letter n there is once again an integer multiplier, just like it was for earlier in this unit on standing waves. And the situation that I've drawn here is obviously when n is equal to 1. When n is equal to 0, that just simply means that R1 and R2 are the same distance away from point P, or S1 and S2, excuse me, are the same distance away from point P. So then therefore, when the path length difference is equal to 0, you always get an antinode. But the path length difference can also be a multiple of wavelengths, and then therefore, when it is, you get an antinode at point P. All of this can be exactly predicted, by the way, mathematically by the trigonometry associated with the pattern itself, but it's not necessary for us to go through those details here. Just recognizing how the pattern works in terms of the path length difference is perfectly fine. Now, this is the condition necessary for an antinode. What is the condition necessary for a node? Well, that then looks like this. All right, so condition necessary for a node at point P. Okay, so once again, here is S1, right here is S2, right here is point P, and then I have, once again, right here R1, and then right here R2. Okay, let me go ahead and form the path length difference once again. Like so, that's this space. Delta R here is equal to R2 minus R1. Okay, now in order to get a node at point P, the following has to happen. For example, let's say that we have right here a sine curve that is coming out of S1, and at some instant in time at point P, a crest arrives. Well, therefore, in order to get a node at point P, at the exact same time from a wave that originally started at S2, what has to arrive at point P at that moment in time is a trough. So you have a crest from the wave coming from S1, and a trough from the wave coming from S2, and they cancel each other out completely, and then therefore you end up with a node. The water is completely flat. In order for that to happen, coming from this point right here, which is once again the same distance away from point P as S1 is, you have to have a wave that is pi radians out of phase with respect to this wave here. It has to look like so. So this guy here, 180 degrees or pi radians out of phase with respect to this guy here, they would then cancel each other out when they arrive at point P together. In order for that to happen, right here in the path length difference, you have to have a half a wavelength, or 1.5 wavelengths, which for example would look like this. I know I'm kind of fudging this a little bit. Right here is 1.5 wavelengths, or 2.5 wavelengths, 3.5 wavelengths, etc., etc. So then therefore the condition necessary to end up then with a node at point P is written in the following way. You have to have odd multiples of half wavelengths. Here's how this 2n plus 1 odd multiplier works. For example, when n is equal to 0, then you end up with a 1 here in parentheses, and then therefore the path length difference is a half a wavelength. When n is equal to 1, this is a 3, which would be 1.5 wavelengths. When n is equal to 2, this would be a 5, which is 2.5 wavelengths, and so on and so on. So the 2n plus 1 here is referred to as an odd multiplier. Sometimes some textbooks, by the way, will take the 2 in the denominator here and then factor it in, like so, into the commas, or into the parentheses, rather. And when you do, you end up with this expression here, and it of course means exactly the same thing as this. It kind of depends upon the textbook that you're looking at in terms of how they're actually going to write the expression. I believe your textbook, however, writes it like this, and that's how I prefer to do so as well. Once again, all of this can be predicted by the trigonometry. It is not necessary for us to go through this here. Now, we introduced this two-source interference pattern to you here in the context of water waves because you can easily see the interference pattern itself in the means of the short video clips that I've posted for you, and it's also pretty easy to explain mathematically, even though it does look, initially at least, horribly complicated. The reason why we introduce it here, however, is for the following. We will see a little bit later on the exact same interference pattern, but we will see it associated with light, okay? Okay, that now concludes part 2 of this lecture on water waves. At this point, make sure that you are working steadily on the next problem set. Pay close attention for the due date for that problem set. Today's shirt, by the way, is from The Sword. See ya.